لو أخذت الطيف اللي جايني من كوكب بي مثلا أو سي، كل كوكب يعكس ضوء الشمس، فالضوء اللي جاي من الكوكب لو أخذته إلى منظار ثم إلى منشور سيتحلل اللون اللي منعكس من الشمس إلى ألوان الطيف. إذن ضوء الشمس هو اللي بيعطيني كل الألوان، لكن اللي بلاحظه إنه في خطوط سوداء. لو جيت كبرته بهذا الشكل سأجد أن هذه الخطوط السوداء اللي شايفينها كل واحد يسمى خط امتصاص أو طيف امتصاص خطي. إذن هذا اسمه طيف امتصاص خطي وهذا طيف امتصاص خطي. عدد الخطوط بدلني على العناصر المكونة لهذا الكوكب بي. فمثلا لو جيت أقارن هالخطوط اللي امتص الكوكب من الضوء المتصل واللي سميتها باسم طيوف الامتصاص بغاز الهيدروجين، نلاحظ ما يلي: هذا إصدار غاز الهيدروجين، إذن هذا طيف إصدار خطي، هذا الأسود طيف امتصاص خطي. أجد أنه فعلا الكوكب عليه نفس الخطوط الهيدروجين، هذول طيف إصدار هيدروجين، إذن هذا الكوكب يحتوي على هيدروجين. لو قارنته بالصوديوم ولغيت الهيدروجين أجد أنه لا يوجد امتصاص في الهيدروجين، عفوا في الصوديوم، يعني هذا خطين الصوديوم تمام ما ناقصين هنا، ما في خط أسود، إذا لا يوجد على الكوكب صوديوم. لو أخذت الحديد لا يوجد حديد. أخذ الزئبق لا يوجد زئبق. أخذ الأراغون، لاحظوا معي هذا الكوكب امتص طيف الأراغون، إذا يوجد
We know that if I heat an object, it is going to give out some kind of radiation, right? Like a flame, for example, or a piece of hot metal. Now, if I take this hot metal, so let me take an incandescent light bulb, which is basically nothing but a heated tungsten filament, right? And that's giving out some radiation in the form of light. If I take this light and pass it through a prism, and I keep a screen behind, what will I get? I'll get a continuous set of colors, right? Or a continuous spectrum, correct? Something like this. Now, if I change the source to a fluorescent lamp or a mercury vapor lamp and then perform the same experiment, I find something very different. On the screen, I find only certain wavelengths or certain colors. But in the previous case, I found a continuous spectrum of wavelengths or colors. Now, what was the difference? In the first case, I heated a solid, a tungsten filament. In the second case, I was heating a rarefied gas, in the case of a mercury vapor lamp or a fluorescent lamp. So when I heat a rarefied gas, I get only a set of wavelengths on my screen. And this spectrum, this is called the emission line spectrum, and these lines are called spectral lines. It was also found that this set of spectral lines was characteristic for a particular element. Or in other words, an element always produced the same set of spectral lines. Also, it was found that when white light was shined through this element, the spectrum that was observed did not have a few frequencies, or there were a few dark lines. And these dark lines corresponded exactly with the spectral lines that we saw in the previous case. This basically means when a gas emits some radiation, it emits only a few frequencies. And when light is passed through a gas and it absorbs some radiation, it again absorbs only few frequencies and exactly the same frequencies that it emitted in the previous case.
Star. This is called a transit. During a transit, some of the star's light travels through the planet's atmosphere and gets absorbed. The light that survives carries information about the planet across light years of space where it reaches our telescopes. However, the planet is very small relative to the star, so it is still very difficult to detect, which is why we need a big telescope to be sure to capture this tiny bit of light. So how do we use a telescope to read transit light? Stars emit light at many wavelengths. Like a prism makes a rainbow, we can separate light into its separate wavelengths. This is called a spectrum. Visible light appears to our eyes as the colors of the rainbow, but beyond visible light there are many wavelengths we cannot see. Now back to the transiting planet. As light is traveling through the planet's atmosphere, some wavelengths get absorbed. Which wavelengths get absorbed depends on which molecules are in the planet's atmosphere. For example, carbon monoxide molecules will capture different wavelengths than water vapor molecules. So when we look at that planet in front of the star, some of the wavelengths of the starlight will be missing, depending on which molecules are in the atmosphere of the planet. Learning about the atmospheres of other worlds is how we identify those that could potentially support life, bringing us another step closer to answering one of humanity's oldest questions: are we alone?
If a sample of hydrogen gas is heated, it gives off light. When you view this light through a prism, you'll see an emission spectrum consisting of bright lines at specific frequencies. Because the spectral lines come at definite intervals, this suggests that specific energy levels exist in the atom. A cross-section of an atom shows the energy levels similar to the rungs of a ladder. When energized, the electrons move temporarily to higher energy levels. As the electrons fall back to lower energy levels, they lose energy in the form of light, which produces the characteristic spectrum of the element. Because we know that the emission spectrum for each element is different, we also know that the distances between energy levels must be different for every element.